All right, and here's the last part, chapter 15, part 6. So this will be the last thing for the rest of the year. All right, so the path of a reaction and the effect of a catalyst. Most of you guys should have already learned what a catalyst was back in biology. And the way that they teach it is pretty accurate. They just don't tell you why it's happening or what is causing it. And so the equilibrium constant describes how far a chemical reaction will go. The rate of the reaction describes how fast it will get there. So just because a reaction makes a whole lot of product doesn't mean that the reaction will get there quickly. Some reactions can take thousands of years for them to actually get there. The activation energy or activation barrier for a reaction is the energy barrier that must be overcome in order for the reactants to be converted into their products. So we talked about this at the very beginning of the chapter. So if this is the hill that the reaction has to get up in order for the reaction to go. So if it can't get up this hill, then the reaction can't go anywhere. And so that's the energy of activation, is that hump. And the activation energies exist for most chemical reactions because the original bonds have to break before the new bonds can begin to form, and it requires a certain amount of energy. You have to put energy in to break bonds. That is where chemists and biologists, we don't disagree, we agree, we just say it differently. So if you're taking a biology class and they're saying that breaking bonds releases energy, they're incorrect. If you're going to break a pencil, you have to put energy into it. If you're going to break anything, energy has to be put in to break it, right? If you're going to get mad while you're playing a video game and you're going to break your controller, energy has to be put into that controller in order to break it into pieces. There's the same thing with molecules. In order to break a bond in a molecule, energy has to be put into it. Now, when we make new bonds, the opposite is true. Energy will come out. The overall thing for this part is the activation energy. That's what we're looking at. So if this is where we start the reaction, and this is where we finish the reaction, this reaction overall has lost energy. But that didn't change the fact that we had to put energy into this to break those bonds. We just happened to get more energy out when we made these. And so overall, we got energy out. So the activation energy is this hump right here. And so we have to get over that hump. So for chemical reactions, the higher the activation energy, the fewer number of reactant molecules that make it over the barrier and the slower the rate. So the bigger that activation energy hump is, the harder it's going to be for more molecules to get over it. And so the longer the reaction is going to take. Are there any ways to speed up a slow reaction? Well, we can increase concentration of the reactants, which makes more collisions occur, and it increases the rate. Or we can increase the temperature, which causes the reactants to collide more often because they're moving faster. Or we can use a catalyst, and that lowers the energy of activation barrier. So when we look at how a catalyst works, without a catalyst, these reactants, or this hill, or whatever this is supposed to be here, have to get over that hill and then they can fall. But if we put a hole through the hill, then they don't have to go as far. And so it doesn't take as long. And that's basically what happens when we use a catalyst. It goes a different way. The reaction has a different mechanism that it goes through in order to achieve the product. So it's not taking the same route that it had before. And so it lowers the energy of activation. So instead of having the big, huge hump, we only have a very small one. And therefore, the reaction proceeds more quickly. And this is how enzymes work. So if we look at real world situation, this is ozone. That's the gas that's in our ozone layer. And if it reacts with an oxygen atom, it will create O2. Now, this reaction written like this is not very productive. It doesn't really achieve much product because it's a very, very slow reaction. But if we add chlorine atoms to ozone, it acts as a catalyst and it will destroy our ozone layer. And those are put into the air by chlorofluorocarbons. And fluorine can have the same effect. And we use these a lot in like freons and stuff like that. So stuff that makes our air conditioner cold. And some accelerants in aerosol cans and stuff like that. I don't think they use them as much anymore. But that's basically how we've destroyed parts of our ozone layer, is those chlorofluorocarbons getting up into our upper atmosphere, and then it catalyzes this reaction and forces it to occur. One thing, a catalyst does not change the position of equilibrium. It doesn't change how much reactant or how much product gets made. It just makes it happen quicker. So biological catalysts are enzymes. Sucrose is broken down into glucose and fructose, and we use sucrase, our body does, in order to do that. That's the enzyme. And so it takes a shorter method, a shorter mechanism in order to achieve the product. And the way that it works is, this is the enzyme, this big, huge thing here. And there's only one little bitty part where sucrose can fit in there. And so this whole thing here is sucrose. And what it basically does is it kind of pulls them apart and weakens the bond between sucrose, because sucrose is table sugar, and it's made from a glucose molecule and a fructose molecule bonded together. And so over here on the left, this bond that holds the glucose and fructose together gets weakened, and then we can break it faster. And so these enzymes kind of manipulate the molecules in a way to make them more accessible.